In this video, I'm going to be introducing this idea of piecewise functions by just breaking it apart and just dealing with segments and rays individually. So in this video, we're going to be writing equations of rays and segments and graphing equations of rays and segments. To draw a segment, we're dealing with vertical and horizontal lines, or we could have a diagonal segment. We also got to deal with what's called the domain or the range, depending on whether it's a horizontal or a vertical segment. So x values that constrain or cut off a line and just focus on a certain portion, they're called a domain. If I'm describing y values that do the same thing, that's called a range. So this is saying we have a horizontal line at y equals -7, but only in between x values that are -4 and 5. So we can find our -4 and +5 on the x-axis. We know that our segment is going to exist between those two, and it's a horizontal line at y equals -7. So I can plug in any of these values on the x-axis into my function, and I will always get -7. It's a constant function or a horizontal line. But I can't plug in anything more negative than -4 or more positive than +5. That does not exist in this graph. So similarly, if we have a vertical line, that's going to be an x equals equation. It would be x equals 6, or it would intercept 6 on the x-axis if it continued forever. But this vertical line or segment is really only existing for y values that are in between 2 and 8. So if I can find 2 and 8 on the y-axis, my graph exists between those y values, but not beyond. A diagonal segment is a little bit trickier. We're going to use a slope-intercept form of a line, y equals mx plus b. We can start at the y-axis at +6 and use our slope to graph the line lightly, but we're only going to draw the line for x values that are in between 4 and 9. So this line exists only for x values that are in between 4 and 9. Beyond that, we got to erase whatever we sketched before or just not draw it to begin with. So if I plug in 5 into this function, I get -5 plus 6, which is 1. So that exists on my line. I could plug in 8. So -8 plus 6 is -2. So at 8, -2, that's also on my graph. So any x values that are in between 4 and 9, I can plug in and evaluate and get a y value and plot those points. Anything outside of that does not exist on this segment. We can think about that backwards. Given the graph, can we write the equation? So this is going to be a horizontal line. That's a y equals 1 equation, but for only existing between the x values of -2 and +2. So we state our domain. It's y equals 1, except it only exists in between -2 and +2. For a vertical line, we're going to use an x equals equation. So this is x equals 3, but it only exists for y values that are between -4 and +2. And when we state a range, we work negative to positive, similar to a domain where we work negative to positive. So we're working left to right when we describe values that exist, or we're working bottom to top. Another diagonal segment. We can use point slope form rather than tracing the graph to find the y-intercept. Sometimes that doesn't always work. We could start with point slope form because I know at least 2 points, the endpoints are on our graph. So I chose -5, -9, and I plugged it into point slope form. So y minus -9 turns into y plus 9, and x minus -5 turns into x plus 5. And we can visualize the slope, or we can actually find the slope between the 2 points, and we find that it's 2. So we can start with our point slope form, convert it to slope-intercept form, and we get y equals 2x plus 1. Then we can verify on the graph, and it looks as if it's going to cross the y-axis at 1. But this graph only exists for x values that are in between -5 and -2. So there's our domain constraining this graph. It only exists for those x values. Let's draw a ray this time. Rays are a little bit different. So this is still a horizontal line, but it only exists to the left of 3, or for x values that are less than 3. So y equals -4, but only when x is less than or equal to 3. So it moves to the left. For the vertical line, we got x equals 2, but it only exists when our y values are greater than 1, greater than or equal to 1. And for a diagonal, we could start at 3 on our y-axis, count down and right 3, and we can do that backwards, left 3, up 1. And we could sketch out our ray or our line first, and then determine that it's a ray because it only exists when we move to the left of -3. So it only exists when x values are less than or equal to -3. The right side of this graph no longer exists, so we just have a ray pointed to the left. We could write equations given the graph first. Again, we got a horizontal line. So y equals -3, but it only exists to the right of 4. So y equals -3 if x values are greater than or equal to 4. A vertical line, we got x equals -5, but only when y values are less than or equal to 3. And one more time with the diagonal, a little bit trickier. Here's an example where if I try and trace my graph using my slope, I intersect my y-axis in between two whole numbers. So I really need a more specific way of writing my equation. Again, I'm going to use point slope form. I know that this endpoint of my graph is going to lay on my graph, so I can use it. So if I use 1, -4, then I have y minus -4, which is y plus 4, and I have x minus 1, and I can look at my slope, or I could choose 2 points on my graph and evaluate my slope. The slope of this is -1/2. So I could draw my line, but I want to figure out what that intercept is. So use point slope form to write the slope intercept form, and we could distribute -1/2 and subtract 4, and we end up with y equals -2x minus 3.5, or y equals -2x minus 7/2. So then we can verify that yes, it is crossing in between -3 and -4. But this line only exists to the right of +1, so only if x values are greater than or equal to 1, and that gives us the ray. That leads us to actual piecewise functions. So the only difference here is slightly different notation. F of x is function notation for y, so this really just says y equals 3. So this is just a horizontal line at y equals 3, but only for x values that are in between 2 and 6. And now we got a slightly different notation on our inequalities. It includes +2, but it does not include 6. So at x equals 2, we have a closed circle. It includes 2. At x equals 6, we don't include 6, so we leave an open space or an open hole there. So we have a horizontal line in between 2 and 6, but we're including x equals 2 and not including x equals 6. We also have another horizontal line. This is y equals -4 as well. But in our domain, we're including -3 and not including 2. So in between -3 and 2, at y equals -4, we're including x equals -3, but not including x equals 2. And we got one more horizontal line, so just 3 horizontal lines here using fancy function notation. So y equals -8, but only in between -8 and -3, and we don't include either of those endpoints, so we use open circles at the ends of that segment. If we want to combine it with a segment and array, you may see something like this. This is y equals -x plus 1. So I can start at 1 and go down 1 over 1, down 1 over 1, and draw it lightly, and realize that I'm only drawing this line for x values that are greater than or equal to 3. So nothing to the left of 3 is going to exist on this line. I can erase it. So we just have a ray pointed down for x values that are greater than or equal to 3. And then we also have a horizontal line. We got y equals 2, but in between -7 and 3, and then we include -7, but we do not include +3. So horizontal line at y equals 2, in between -7 and 3, not including 3. So there's piecewise functions, which is just a fancy way of drawing segments and rays.